this experiment, I will demonstrate how you can boil water using your bare hands. We start with a closed container which contains water, or H2O. I place it on an electric coiled range, which heats the container and boils the contents. Let us define boiling. Boiling is the act in which the pressure of the air is equal to the pressure of the gas within the container. By increasing the temperature of the contents, I also increase the pressure within the container. When the pressure reaches about 101.3 kilopascals inside the container, the water boils. Knowing this allows the experiment to be performed properly. Now the container is placed on a non-heated surface, so it can make it easier to perform this experiment. Ice water is critical for the process because the cold hands lower the pressure inside the container, which makes the temperature lower, and the lower pressure results in a lower boiling point. This has been a demonstration of boiling water by decreasing pressure.
In this experiment, you will witness how a soda can be crushed in cold water. First, the can is placed on a hot surface, preferably a hot plate, but in this case, a grill. As the can heats up, the gas within the can expands. According to Charles's law, temperature and pressure are directly related. Now the air within the can is at a very high pressure. Watch what happens when the can is placed into the ice water. The reason for this is, again, due to Charles's law. The ice water is at a much lower temperature than the air within the can. When the can was placed into the water, the temperature was dropped, and consequently the pressure was too. With the pressure being lower than the outside pressure, the can crushed. This concludes the soda can demonstration.
In this experiment, I will show how static electricity can bend water. Here we will use a comb, a faucet, and a head full of dry hair. First, you need to turn on the water faucet to a very thin stream of water, making sure that it does not touch the comb. Now we are taking the comb and just slowly bending it near the water. If all goes well, the stream of water should bend toward the comb, which it is, as you can see. How does this work? When you brush a comb through your hair, tiny parts of the atoms in your hair, called electrons, collect on the comb. These electrons have a negative charge. Now the comb has a negative charge. It is attracted to things that have a positive charge. It is similar to the way magnets are attracted to metals. When you bring the negatively charged comb near the faucet, it is attracted to the positive force of the water. The attraction is strong enough to actually pull the water towards the comb as it is flowing. The reason for this is due to the polarity of water. As shown in this diagram, the O is negative, while the H's are positive. This causes the bend effect. This has been a demonstration of water polarity.
The video was really good. I hope we get some recognition for it.
I agree. It was put together very well.
Truly a chemical masterpiece.
I agree. Now, we should go back to my office. We need to resume some work.
I concur.
Very well. Hello, Chemical Labs Department. Oh, hello, Jack. What's the problem? What? Alright, I understand. I'll arrive with my team as soon as I can. Bye. Well, that was Jack from the bomb department. He has some bad news. Apparently, a week ago, someone placed a bomb at the chemical facility and on one of the cesium tanks. Tomorrow morning, we're going to head out to the chemical plant and see what we can do to defuse the bomb. Because in this area, we're the best. And Jack really thinks that we'll be able to do it. So, tonight, we're going to get our stuff together, and then we're going to head out tomorrow morning. The door's not opening properly. Try to see if you can get his manual or something. Freeze! Oh, see, we were trying to get in here because I don't have my pass, but if I get my ID out, you know, I think I'll be alright. Here you go.
That was one deadly reaction.
Alright, I traced his path. He's gone from here to this door. This is where we need to go. Alright, so let's go. Yep.
This place is a mess.
I agree.
Wow, whatever happened here? Everything is destroyed in here. We gotta find the chemical room. Do you hear that?
Yeah.
It's coming from in here. This has gotta be where it's at. It's gotta be in here somewhere. This is all Jack told me. Where would he have put it?
Are these the tanks?
Yep. That's right. These are the tanks that are gonna blow up if we don't figure out what the bomb is. Wait a minute. Look. It's the bomb. It's the bomb, alright.
It seems the bomb is hooked up to the H2O line. That means the cesium would react with the water.
Alright, that makes sense.
That would be a deadly reaction.
Alright, let's see. This should be really easy to take off. Oh. Alright, bad idea. We gotta get out of here right now. It's self-destructed. Now, let's go. Let's go. Right now. Come on. All the time.
The reaction wasn't as bad as I thought.
Yeah, nowhere near as bad. But still, we now know the effects of cesium and other alkali metals in the effect of water.
But still, a deadly reaction.